Good evening, everyone. Myself, Vasudha Sharma, and I'm a PMR fellow at Department of Chemistry, IIT Bombay. And here it's the V2 NPTEL live session for the course Circular Dichroism and MOSPAR Spectroscopy for Chemist, taken up by the Professor Arnav Datta. And here we will be discussing the lectures that have been covered in week 2 and some basic concepts regarding that, and any clarification that you want regarding the week 1 lectures or in week 2 lectures. And correspondingly, we'll be having assignment problems. So to make you more comfortable with the concepts that have been covered so far. So we will be waiting 3-4 more minutes for others to join, and then we can start with the lecture. Thank you. So, in the last live session, we discussed a lot of points regarding symmetry elements and how it is related with the chirality, how it is related with the symmetry operations and different kind of point groups. And we discussed a lot of them. And in the last live session, I gave you guys some homework to find out what would be the symmetry elements and the total number of symmetry elements present in H2O2 open book form. And the second question was to find out the number of improper rotational axis operations in case of S4. So we will quickly take up these two questions and then we can move ahead with the new things. So as I was explaining that firstly, this H2O2, this exists in three forms: cis, trans, and open book. Open book is nothing but just like you can also consider the open laptop. So that would be more clear to you. So cis form, we have already considered that in cis form, we were having both. So in cis form, we were having oxygen and oxygen. Both the H, the hydrogens, they are facing towards each other. So this is nothing but your cis form. Then in trans form, hydrogens are in opposite directions to each other. So this is trans. And in open book form, so we have something like this. I will try to make it more so that you can understand. Consider this as your laptop or something, book or your laptop. So here your oxygen bond is here, and one H would be this direction, one H would be this direction. So this is your open book form. So we already discussed in the last live session that says H2O2 was having how many symmetry elements? That was having a point group of C2V, so giving 4 symmetry elements. Trans was having C2H, giving you 4 symmetry elements. And open book, we need to find it out. So for the open book thing, we need to know so in case of open book H2O2, so as I said that so here is your oxygen bond, and one H is here, one H is here. If you will see that it can only be having identity which is present in everything, and one more operation is possible over here, which is C2, that 180-degree rotation along your OO bond, oxygen bond. So if I will mark it as A, this as B, C2 180-degree along oxygen bond, it will give you HP above and HA down, which is equivalent conformation. So therefore, only this particular symmetry element is present, which is nothing but your proper axis of rotation. So if you can consider whether we are having a plane or not, this is not a simple molecule which is having a plane and one side is other, one side would be reflected by this. If you will see over here, the open book would be like this way. So this is my notebook and this is open like this particular form. Even if I try to put a plane over here, the hydrogens won't be, because one hydrogen is this direction, one hydrogen is this. So there is no case that it can be having any plane of symmetry. So no plane is there, no invergent center is there. So it is only having the C2 point group. That point groups we'll discuss in next slides. But for the C2 point group, it is only having total number of elements as 2. So number of elements, symmetry elements present in case of open book H2O2 is 2. So now our answer here becomes that because of the C2, it is only having 2 symmetry elements. That is the order of this particular open book is equals to 2. So this is the answer is 2. Now we need to understand, as we discussed about S5 or S3, I think in the last live session, and we need to find out how many a number of improper rotational axis operations are present in case of S4. So here we will be taking up this thing. So we need to find out number of improper rotational axis operations in case of S4. So as I have already told you that Sn is equals to Cn into sigma h. That sigma h is perpendicular to your Cn, that proper axis of rotation. So if I'm taking S4, it would become S4. That is with respect to this n, that would be C4 into sigma h. That sigma h is perpendicular to your C4. Say for example, I'm taking a z-axis where the C4 is along the z-axis, and sigma h would be your sigma xy. So considering that S41 operation, we have to do the operation until unless it comes to your identity. So S41 would be C41 sigma h1. This is nothing but this has to be considered. So it would be taken as, because C41 into sigma h, there would be a certain operation. Then S42 would be C42 into sigma H2, that C42 is nothing but your 180 degree. C4 is 90-degree rotation, whereas C4 two times, that is 90 plus 90, that will become as 180. So this is nothing but your C2, and sigma H ka square will give you identity that is equals to C2. So C2 is no more, the S42 operation is no more sorry, improper axis of rotation. It has become now C2 symmetry, which is already existing in your system. So next one is S43, C43 into sigma H3. Now C43 would be your 3 times when we are having something like 180 plus 90 degrees, that is 270 degrees. So this operation will exist as such. And sigma H3 would also be existing as sigma. So one time plane of reflection, then another, then another. So 2 times will become identity, and the last we'll get a sigma. So this also will be considered. Next one is S44, C44 into sigma H4. Now C44 is nothing but your 360 degrees. So when you are rotating 90 degrees 4 times, that will come as a 360 degrees. And sigma H4 is also E identity. So identity into identity is equals to identity. Now we have achieved identity. That means we do not have to go any further. So for S4 operation, you can see for S4, only S41 and S43 can be considered as your number of improper rotational axis operations. So it is only giving 2 operations. So the answer for this question now becomes, answer is 2, which is S41 and S43. So this is your answer from the last live session questions. I hope you guys have understood that. Now we are moving towards, as I said last time, we promised that we will be discussing about the tetrahedral and octahedral symmetry elements, which is very important to understand because they are having the highest cubic symmetry. So that we will take into consideration now. So for example, I hope the slides are visible. So here, as you can see, I have written the tetrahedral symmetry, which is the cubic group. These groups we have already talked about last live session. Also, the professor has talked about it in detailed explanation he has given. So here you can see, we know that 24 symmetry elements are present in tetrahedral symmetry. And these are the elements which are present in your tetrahedral symmetry. So the structure that I have drawn over here, you can see. So this is some molecule, which is actually, this is methane molecule, which is having a tetrahedral symmetry. Having geometry is one thing, having a symmetry is another thing. So even if, for example, we can talk about that CHCl3, that will call as a tetrahedral geometry, but geometry and symmetry is a 2 different things. So it is having a tetrahedral geometry, but it is not having tetrahedral symmetry. So we have to be very careful what terminology we are using. So here we are saying CH4 is having both tetrahedral geometry as well as symmetry. So that is another case. But here we are talking about the tetrahedral symmetry. So in tetrahedral symmetry, this comes under a cubic point group, which is having highest symmetry. So they are very symmetrical in nature. So here we need to find out the number of symmetry elements that it involves at 24. That is a high number. So here, if you will see, this is your carbon, which I have highlighted with green. And here is one hydrogen, Ha. This is Hb, Hc, and this is Hd. So this is a combination of where all the Ha, for your information, Ha, Hb is equal only. I've just highlighted it. Like, to make a clear picture to you guys, I have just given a notation to it. So if you will see here, how many vertices we have. To define the number of symmetry elements, we need to understand what kind of symmetry it is having, which is related to the geometry also. So here, the vertices are 4 in number. Vertices are nothing but wherever you are having. If I'll draw it like this way. So vertices are these ones that I'm highlighting with pink on the hydrogens. These are your vertices, like on the tetrahedron side or in a cube. When we talk about something like this way, so here, now my carbon is here. It would be connected to one hydrogen at this side, one hydrogen at this side, one at the back, and I'm showing a one over here. So this is a kind of tetrahedron that it would form. In a cubic structure also we can explain like that way. Now, so vertices are 4 in number. If I'll talk about the faces that are also 4 in number, what are the faces that I'm talking about that I'll explain? And the edges are 6. So edges are, which are the pink dotted one, pink dotted lines. These are your edges. So these are 6 in number. This is 1, this is 2, 3, 4, this is 5, and this HD and HP, that is a 6, which is binding to your carbon. So now we know that vertices are 4, faces are 4, and edges are 6. So for faces in that aspect, I can explain it here. Okay. So in this particular case, as we said, that this is HA, this is HB, HC, and HD we are having. So there would be 4 faces. What are those 4 faces? So the front face would be, or any space, like this is happening like this way. HA and HC. So this is happening like this way. So if I will take my front face as this orange block, this is front face is nothing but your HA, HB, HD, comprising of carbon itself. So the front face is having HA, B, and D. And the bottom face would be your this green in color that I'm highlighting over here. So those who are joining now, it is a request that if you have any doubt at any point of time, you can unmute yourself and ask the question, or you can put your questions in the chat box. I'll be happy to answer your questions. So here we are discussing the lectures that have been taken in week 2 for the NPTEL course Circular Dichroism and Morse power spectroscopy, and we will be discussing the assignment problem. But here today I'm firstly explaining how we get the symmetry elements in case of cubic point groups, which are tetrahedral and octahedral in nature. So if you guys have any problem in understanding, just let me know. So here I am explaining a tetrahedral symmetry where I just said that it is comprising of 4 vertices, which I have highlighted as HA, HB. It's a CH4 molecule that is a methane. So for representation matter, I am giving HA, HB, HC, and HB. Now, if you'll see, the vertices are 4, which are nothing but your atoms. So you can consider one vertex on the one atom. And here I am now explaining the faces. 4 faces are there, but how do we analyze that what faces are these? So the front face, which I have marked with this orange one, which is comprising of H, A, B, and D. The bottom face is your marked with green color, which is HD, HB, and HC. Now, if you'll see the left side is also one face, which is your marked with purple color, HD, HA, and HC. And here I will use a pink marker for defining your right one, which is HA, B, and HC. It is comprising of the carbon also, but for it is not comprising. I'm just telling you about this one triangle, which is it is forming, having a face of it. So these are the 4 faces that we are having in tetrahedral symmetry. Now talking about the edges, I've already talked about edges, which is 6 in number, and you can count the total number of bonds over here. This HA, HD, HA to HB. Now 1, 2, 3, 4, 5, and 6. So 6 edges are there. Why this information is important? Because we will be explaining how the symmetry elements we can generate and how we can understand which symmetry element is passing through what, because this is the kind of complexity has come. It is not a simple molecule or a very less number of symmetry elements are present. So as I explained over here, now you can analyze and can see which would be the firstly we know that it is a non-linear molecule because it is having some kind of proper shape and geometry. So it is not a non-linear thing. So it's a non-linear. Now we need to understand what is the highest symmetry which is present over there. So okay. So firstly, the question is any Cn is existing over here? Cn is nothing but your proper axis of rotation. So along which when we are giving a rotation to your molecule, it should give you an equivalent conformation. Yeah, sure. So I guess you missed the thing. So here I was explaining that I will redraw it for your better understanding. So for tetrahedral symmetry, I hope you understand that cubic symmetry we are talking about, or cubic point groups we are talking about, which comprises of tetrahedral, octahedral, and many more. So we are taking a case of a tetrahedral symmetry, not geometry. For example, if I am taking a case of CHCl3 and I'm taking a case of CH4, both are having tetrahedral geometry. Yes? Is it true? You can unmute yourself. Then only I'll be. Yeah. So it is having tetrahedral symmetry, but are they both are having tetrahedral symmetry? So geometry and symmetry, yeah.
Yes, ma'am, both are tetrahedral.
No, here we have to understand it very carefully that geometry is different from your symmetry. So both are having tetrahedral geometry, that is fine, but they both don't have tetrahedral symmetry, because if I will say symmetry means something that it should generate the same kind of molecule. For example, if I'm applying any operation, I have rotated the molecule, I have put a mirror plane on it, so it should give me a similar kind of conformation, not identical, but equivalent. For example, if in this particular case, if I'm saying that CHCl3 would be this like this structure. This seems to be your tetrahedral, but it is not having a tetrahedral symmetry. Why? If I will rotate it, this is, and compared to this one, CH, H, H, and H. So this comes under tetrahedral symmetry. Why? Because this is having 4 C3s, but here only 1 C3 is there, which is passing through your carbon and H. C3 means that you have to rotate the molecule along an axis. For example, here it is my pen and my axis is this one. And when I am rotating it, the other 3 chlorine would be rotated by a 120 degrees. So these chlorines would be replaced by each other. Chlorine C will replace chlorine A, or chlorine A will go to chlorine B position. So only the change will be observed in the chlorine position, and the axis will pass through this carbon C bond. This is C3. So only one C3 is there. Whereas in case of in this methane molecule, if you'll see, one C3 will go from CH bond. The other C3 can go from this CH bond. The other C3 will come from this CH and this. Because we are having four similar identical hydrogen atoms. So C3 can be possible from any way. So here we are having four C3s. That's why the symmetry has increased. The symmetry is more in this CH4 case rather than the CHCl3. And this gives you a point group of C3b, whereas this is a point group of tetrahedral. I hope you know about the point group or something like that. Anyway, I'm going to explain the point group, but in last live session, we have already talked about the symmetry. What is symmetry? What are the symmetry elements and operations? Do you have that idea about it, or I should explain it more?
Yes, ma'am, I had some idea on it.
Oh, great. So now this concept is clear that why I'm saying that both are having tetrahedral geometry, but they both differ in their symmetry. CH4 is having tetrahedral symmetry, but not CHCl3. Because of the reduction, one hydrogen or one Cl has been replaced with hydrogen, so symmetry change happens a lot. So we can't call them both as having a tetrahedral symmetry. Is that clear?
Ma'am, if number of C3 operation increases, it is tetrahedral symmetry, like that.
Sorry, I can't hear you.
No, I am asking, if a molecule is tetrahedral means it has more number of C3 symmetries. Like that, we have to determine.
Yeah, in case of the tetrahedral, we consider a molecule which is having a complete tetrahedral, like all the atoms are similar, that would be having a tetrahedral symmetry. It would be having more number of symmetry elements. For example, if I have just taken a case of 4C3s, the tetrahedral I'm going to explain. So 4C3, beyond that 4C3, there would be many C2s, then there would be many sigma planes, S4 would be there. So there are many number of symmetry elements, whereas in case of this CHCl3, there is limited number of symmetry elements. That differentiates CHCl3 from the CH4 on the basis of your symmetry. So more number of symmetry elements, you will have a more symmetry. And that higher symmetry comes into a group of cubic point groups, like which are having the highest symmetry. For example, we know that in last live session, if you go back and watch those videos, there also we explained that if A is equals to B equals to C, these are the three sides of your cube. If three are equal, then you call cube as the highest symmetry, right? So if A becomes equal to B, but it is not equal to C, then symmetry will be reduced. There would be some elongation in your structure or something. So that is not called symmetrical anymore. Similarly, if A is not equals to B, not equals to C, so if the total symmetry is gone. Now one length would be high, more, breadth would be less, then the width would be less. So in that perspective, your symmetry, you can't call that as a symmetry. For example, by symmetry term we are using, symmetry is something when we are applying an operation. For example, here I am having this pen, and if this pen, one edge is here and one edge is here, both are looking symmetrical, and on applying any operation, one edge would replace the other one, and they are giving the equivalent conformation. They are not changing anything. They are just changing the position, but they are identical, so we call them an equal conformation. So in that case, when you are having a highest symmetry, that would be considered as a cubic point group, and in cubic groups it would be having the highest number of symmetry elements. We will be taking up many examples later. So is this point clear regarding the symmetry elements and the tetrahedral symmetry?
Yes, ma'am.
Okay. So as you asked that to explain the phases of this one, I will just again take this molecule and explain to you. Okay. So here I have said that HA, just to make sure, this is a CH4 methane molecule, right? So all the hydrogens are same only, but to give a notation, we are just giving as, we are making it as a ABCD so that you should know, you will be able to find out the phases or something. Now to define which symmetry element is passing or having that center, to define that presence or the location of your symmetry element, we need to know that these atoms and how many vertices are there, how many edges are there, how many faces are there. So if you will see how many vertices are there, vertices are nothing but the corners. Corners that if you see this tetrahedron, the corners are nothing but your hydrogen atoms. So how many are there in number?
4.
Right. So similarly, if I'll talk about the faces and edges. So faces we'll explain. The edges I will highlight with the red marker. So this one edge This is not saying that HA and HD are having a bond with each other. No. When we talk about the symmetry, it is different from the geometry. So there is no talking about the bonding. But this symmetry is coming along with your certain shape. When you see the cube, there would be a proper, like I will just show it to you. So this is coming as a form. This is making a symmetry kind of thing. And one bond here and one edge over here. So if you will count 1, 2, 3, 4, 5, and 6. So we are having 6 edges, right? Now talking about the face. So first face, if I'll just make it more clearer. So we need to define the faces. So this is HA, this is B, this is C, and this is D. Now first face, there are 4 faces we are saying. So how do we define our faces? So the first face, the front face is this one. Okay. Anita, the meeting will end in 10 minutes. You have to rejoin the link, right?
Okay, ma'am.
Yeah. So here the
Ma'am,
front.
is that the same link?
Yeah, you have to join the same link. So
Okay,
here,
ma'am.
if you will see, the front face is comprising of A, B, and D. That is marked with orange. The bottom face, the top face and the bottom face is this D, B, C, which is comprising of H, D, B, and C. Now, if I talk about the left face, this is something this blue marker. You have to identify the triangles within that tetrahedron. So this is having DAC, and the other one is marked with your green color, which is ABC. So now the faces are clear to you?
Yes, ma'am.
Yeah. So here we are having the 4 faces. So we have defined the 4 vertices, we have defined the 4 faces, and we have seen that how 6 edges are there. Now the question is, how do we define our symmetry elements? We know that tetrahedral symmetry is having 24 symmetry elements. That means these symmetry elements, when it is applied on a molecule having a tetrahedral symmetry, it should give me exactly the similar kind of conformation that a tetrahedral. So if tetrahedral is having C, H, H, 3 H are there, 1 H is above, after applying every symmetry element, it should give me the equivalent conformation. So as we saw that C3 as it is written, so for location, it is very important. We need to know the location. So from where the C3 is present, is there any C4 present? For example, C4 is nothing but your 90 degrees rotation. So is C4 present in your tetrahedral symmetry? Here, if you see it carefully, C4 is something when I have given a 90 degrees rotation, it will give me equivalent conformation.
No, ma'am, I think it's absent.
Sorry?
C4 is not present.
Okay. Why C4 is not present? Because if you will see here carefully, that this HA and HD, they are planar, right? If something, or you can talk about this one. So explaining about this, 2 hydrogens would be on plane. One would be with this wedge form, that would be above the plane, and other would be your below the plane. So when I'm applying a 90 degrees, they do not give me equivalent conformation. They don't come in the same format. The above will become the planar one, and the planar one will become out of plane. So the planar goes out of plane. So because of this doesn't give me my equivalent conformation that I'm expected to have from a CH4 molecule. So because of that reason, C4 is absent in case of your tetrahedral symmetry. Whereas if you will see that is C3 present, we need to find out which highest proper axis symmetry is present or not. So now if you will see, one C3 is going through your CH bond. So if I consider this as a ammonia molecule, this pen direction is my C3, where the top one is my hydrogen and the bottom one is carbon. Is it visible?
Yes, ma'am.
Okay. So the other 3 hydrogens would be like a triangle form over here. So they would be like a triangle over here. So when I'm rotating is as a 120 degree rotation, all the hydrogens, the 3 hydrogens, they will go and replace their positions. And for example, if I'm highlighting it as A, B, C, and D, now C3 is along my C and HA, that is comprising of both the carbon and hydrogen A. So it will give me, there would be no change in HA, but HD will become HC, HC will become your HB, and here it will become as HD. So they will change their positions. But if you will compare this first image and the second image, are they equivalent or not? First question, are they identical?
Yes, ma'am, both are same.
There is a difference between having an identical and an equivalent. So are they called as equivalent or they are identical?
Equivalent.
Right. Why not identical? Because on applying the symmetry operation, if you'll see careful, identical is something, if my one finger is here, after rotation, the same finger should come at the same position, right? But here, if you will see, this hydrogen, this HD goes to HB place, HB comes to HC, and HC goes to HD place. So the change has happened, but since they are same atoms, we can't identify which one has gone where. But actually, they have gone under certain kind of operation, so they are giving us equivalent conformation. But if I will apply a 360-degree rotation, what I will get? Identical or equivalent?
Identical.
Right. So identical conformation we will be getting on applying the 360-degree, that is called as symmetry element E. That is an identity symmetry element. So this is what we were explaining, that okay, C4 is absent, that can't be, because why we can't talk about the C5 over here? Why we started with C4? Any explanation?
No, ma'am, I don't know.
Okay, so here it is, we for C4 or proper axis of rotation, we need to understand that how many atoms are there. Like for C4 rotation, you need at least 4 atoms for going 90 degrees rotation. So all the 4 can come to their original position or equivalent conformation. But if you see here, the maximum number of atoms coordinated with your carbon, that is only 4. So we can max think of the proper axis of rotation going to C4, that 90 degrees rotation. If there would be 5 something related, like in case of PCl5. So if it is having some kind of geometry where 5 atoms are there, then we first start with the C5, whether C5 is there or not. So here, because of the 4 hydrogen atoms are there, so we first asked whether C4 is absent or present. So we found that C4 is not present because after giving 90 degrees rotation, we are not giving the equivalent conformation. Then we saw that C3 is there. C3 is along what? It is along one vertex. It is passing through one vertex. That is where this vertices plays a very important role. So one C3 going from this particular thing, it is not crossing the C, because this is a 3D molecule, you won't be able to analyze here right now on the 2D image, but it is not passing through your HC. It is just going through H, A, and C, that like this way. And the other 3 would be making a triangle, and it will go and give an equivalent conformation. So if it is passing through one vertex, how many vertices we are having? 4. So we understood that one C3 is passing through our vertex. So we are having 4 vertices. So therefore, how many C3s would be present?
4.
Right. So we will be having 4 C3s present. So that is what written over here, that we have symmetry element as 4 C3, right? Talking about the number of symmetry operations, we'll consider that later. But firstly, we need to understand which elements are present. Now, coming back from C3, we need to see whether C2s are there or not. C2 is something which is giving you a 180-degree rotation. Cn is nothing but where n stands for 360 degrees divided by your angle. Like what angle you're giving. For example, if I'm giving in case of 120 degree, 360 divided by 120 give me an n value of 3, which makes it C3. So this is from where it is coming. So if I'm talking about the C2, it is a rotation of 180 degree. C2 will consider as 180 degree rotation. That means it should pass and the other 2 should go like a flap. Like just because this is the 180 degree angle. This angle is 180 degree. So it should go like a flap. Now, we know that it is written over here, it is passing through any opposite edge centers. So firstly, we need to understand how many edges are there. So as I told that there are 6 edges. And if I am having one C2, this is one edge. If I am highlighting here with this pen, this is one edge. This is the opposite edge to it. Like 4 edge is opposite to 2 edge. And this is my C2. This is passing through two opposite edge centers. This is the edge and this is the your edge center, and it is passing through the opposite ones. And when it is passing through that one, the other two, HA and HD and HP and HC, they will go as a flap. So they will replace their positions but give us the equivalent conformation. So one C2 is along your 4 and 2 edge centers. Is it clear? Hello?